In the last video, we derived this formula for the directional derivative of a function at a point, and I wanted to just take a look at a specific example. So let's suppose that f of xy is just the product, x times y. Let's let p naught be the point -1, 2, and let's suppose that for our direction, let's see, there's my point p naught. Let's suppose that I want to go up and to the left, essentially making a 45-degree angle with this horizontal line, like so. So that's the direction that I want to go in. Let's figure out what's the unit vector that would point in that direction. Now I can see just by inspection that the x component is negative and the y component is positive. Okay. I could work with the fact that this angle, the angle that it makes with the direction of the positive x-axis, is 135 degrees. Or I can just work with the reference angle there of 45. Looks like this is just going to be negative root 2 over 2, root 2 over 2. Okay. Negative cosine of my reference angle, positive sine of my reference angle. Okay, excellent. So now, if I want to parameterize this line that passes through that point, I can do that. I'm going to say that that line is r of s is equal to -1, 2, choosing p naught here as our starting point, plus s copies of negative root 2 over 2, root 2 over 2. Okay. I'm going to go ahead and combine that into a single vector, so -1 minus root 2 over 2s, comma 2 plus root 2 over 2s. Okay, fabulous. Now what I'm going to do is I'm actually going to form this composition, which will be a function of just one variable s, then take the derivative, and then plug in 0, exactly what it says. Okay. But then I'm going to do it again, taking advantage of the fact that I can actually just use the chain rule to calculate this derivative. The advantage of that is that I already know what the individual parts of this function are. I don't have to then take the time to put them together to form the actual function composition. So I just want to work through it both ways so that we can sort of see the advantage of using the chain rule. Okay. All right, if I were to take f of r of s, that's x times y, where this is my x and that's my y. So it's -1 minus root 2 over 2s times 2 plus root 2 over 2s. So I'm going to have to FOIL that out. Not the end of the world, but a little bit tedious. And I can certainly see if I had a more complicated function how it could get pretty tedious to actually work everything out. Let's see. This is going to give me a -2 minus root 2 over 2s minus root 2s, and actually I'm going to just keep a common denominator because I'm going to want to combine them, so minus 2 root 2 over 2s, and then minus, let's see, that's going to give me a 1/2 because it's going to become 2/4 or 1/2 s squared. Okay. Let's just rewrite that in descending order, so I'm getting -1/2 s squared. That's going to be minus 3 root 2 over 2s, and then minus 2. Okay, excellent. So that's my function composition. Now if I take the derivative with respect to s of that, -1/2 s squared minus 3 root 2 over 2s minus 2, that's going to give me -s minus 3 root 2 over 2, and of course the derivative of the -2 is 0. Excellent. Now, according to this, we're supposed to evaluate that when s is 0, because of course when s is 0, that's what puts us at that starting point. That's what puts us at p naught, and that was what we wanted to evaluate. Okay. So, the derivative of f of r of s evaluated when s is 0, Not really necessary for me to say that s is 0 here. I could just say evaluated at 0. Should be understood that I'm plugging that in for s because that's my variable. I'm just being a little bit extra redundant here. Okay, but if I plug in 0, that kills off this term. I'm going to get negative 3 root 2 over 2. Okay, I'm going to just write that up here because we're going to do this problem again, and we better get the same answer. Okay, so that tells us that if I'm moving in this direction as I pass through this point, my z values are going to be decreasing, because this is negative, and decreasing at this rate. The z values are going down 3 root 2 over 2 for every 1 unit of arc length that I travel. For every, not 1 unit of arc length along the curve, for every 1 unit that I travel in this direction. Okay, excellent. So, we've got that. Now, let's do this again, but let's not bother to spend the time coming up with that formula. Let's just take the derivative using the chain rule. Okay. So, we'd be saying f is spitting out a z value that depends on x and y, each of which in turn depends on s. Okay. So, chain rule, we're going to get the partial of f with respect to x here, and the partial of f with respect to y here. And at this level, it doesn't make any difference whether I say partials of f or partials of z, because there are no variables that occur on more than one level. There's no ambiguity there. Here, this would become x prime of s, and this would become y prime of s. So, dz by ds, which is the same as the derivative with respect to s of f of r of s, is partial f partial x, x prime of s, plus partial f partial y, y prime of s. All right, so now let's see what these things are. So the partial of f with respect to x is just going to be y. X prime of s, here was x, I can see its derivative is just negative root 2 over 2. You'll notice that's just the x component of my direction vector. Remember, the derivative of a line is just the direction vector for that line, so the derivative of the x component of a line is just the x component of the direction vector. All right, partial of f with respect to y, that's just going to be x. Y prime of s is just the y component of s, so that's root 2 over 2. Okay, so we've got, this is now our formula for the derivative, and of course, if I were coming up with the formula and that was my final answer, I would want to express it in terms of s. I'm just going to take a slight shortcut here. I know I want to evaluate this when s is 0. Now, I don't see any places for me to plug in 0 for s, because s didn't show up in my formula, but I do know that when s is 0, we're going to be at our starting point. We're going to be at negative 1, 2. So I can say the derivative with respect to s of f of r of s when s is equal to 0, which is when xy is equal to negative 1, 2. I'm going to plug in 2 for y, so I'll get 2 copies of negative root 2 over 2. Plus, we'll plug in negative 1 for x times root 2 over 2. And that's going to give me negative 3 root 2 over 2. So I do get the same thing either way, but you can see it was a lot faster when we used the chain rule. Now, it can get even faster than that. Okay. Because we have mentioned that any time we use the chain rule, we're actually just taking a dot product. Okay. So, if I take a look at the derivative with respect to s of f of r of s, looking at it at this point right here, I can pretty much see That's partial of f with respect to x, partial of f with respect to y, dotted with x prime of s, y prime of s. Now this is the version that would generalize and be true even if this wasn't a linear function. That's the gradient of f dotted with r prime of s. But it gets even better because our r was a linear function. So when we looked at what the components of the derivative were, they were just the components of our direction vector. So this is just the gradient of f dotted with u. Okay. So that's going to be my nice, nifty shortcut to calculate the directional derivative. I take the gradient and I dot it with the unit vector that gives me the direction. Okay. Now, this is just my formula for the derivative. The derivative with respect to s of f of r of s, evaluated when s is equal to 0, that's going to be the gradient of f at p naught, dotted with u. Because remember, we parameterize our line so that when s is at 0, we're at our starting point. Okay. So that's generally how I am going to calculate my directional derivative, by just dotting the gradient at the point I care about with the unit vector that gives me the direction. I will just caution you, directions can be specified a number of ways. So I could give you a direction by saying, here's a unit vector, use that direction. But I could give you a non-unit vector. That still specifies a direction. That just gives you a little bit more work because you would have to normalize to get to a unit vector first. And in the name duf, what goes here is always a unit vector. So if I were to give you, say, I want the directional derivative in the direction of 4, 5, I wouldn't put 4, 5 here. I would normalize it, put the unit vector that gave me that direction in the name here. Okay, so this is duf at p naught. Excellent.